Today's speaker is the Rutgers Experimental Mathematics Seminar is Professor Tewodros Amdeberhan from Tulane University, who will talk about combinatorics, classical mechanics, and symplectic geometry. Thank you.
Okay, thank you, and I'm really pleased to be here and get a chance to speak in front of you virtually. And I was planning to do this for a while. Finally, it happened, although online. All right, so try to see if you can remember this page. It will appear here and there. So classical mechanics can be formulated in different ways. There is Newtonian formulation, Lagrangian setup, or Hamiltonian. Will follow Hamiltonian. And for this, we need a phase space, so coordinate space. And this has two sets of pairs of coordinates, n of each, and the q's and the p's. In mechanics, these are position and momentum coordinates. And x will be always this pair of two n coordinates. And the Hamiltonian equation relates coordinate chart with a function called Hamiltonian, and this is a system. And remember, this is a first order. This is a system of first order differential equations, and the H is called the Hamiltonian. Depends on positions and the phase space defined, and also possibly time. And in relation to this, I just highlight some of the relevant things in classical mechanics and soon in symplectic geometry. There is the notion of something called Poisson bracket. It's defined as this, it's like a bracket that not curly bracket, a square bracket for matrices. And it behaves similarly to that for sure. And it has a number of properties: bilinearity, antisymmetry, and the Jacobi identity. And out of this, the only thing probably you will not remember much, just we remember that in this function space, the Poisson bracket makes it a Lie algebra. And typical classical examples are matrices with a usual bracket A, B, minus BA, and also in the Cartesian coordinate system, the cross product is an example that makes it a Lie algebra.
And you use a physics notation. It might be a sigma here, right, for mathematicians, or it's not?
Which part?
The Poisson bracket. Doesn't it have to be a sigma?
Oh, this one. Yeah. Oh, by the way, I'm glad you reminded me. This is
the Einstein notation, whatever it's called.
Yeah, Einstein convention. Thank you. Yes, yes. This is a lot of summation. Yes, thank you. And the Poisson, this will help you translate the Hamiltonian equations into Poisson formulation. We don't need to follow too much into this. The only thing probably we should see is that when the Poisson bracket of H is taken with itself, a Hamiltonian, then there's a constant of motion because derivative is 0. And this notation of Poisson is quite convenient and actually had a good foresight because it helps quantum mechanics to be related this way, although we'll not go into that. And then on this page, I'll just go all the way to the end. The only thing I like you to keep in mind out of this is there is a certain matrix called J. It's a twisting matrix. Then the Hamiltonian equation, this is the highlight on this page. The Hamiltonian equation, on the left-hand side, you have derivatives. And J is this matrix identity here under below the diagonal, negative identity. and then it's a 2n by 2n matrix, and times multiplied by the Jacobian, the gradient of the Hamiltonian. So you can, one might think of this Hamiltonian equation like a gradient equation, but it's not quite. It is a symplectic gradient equation because J rotates everything in each direction, in each pair of directions by 90 degrees. So with that in mind, at least we can write it in this formulation. It looks compact. All right, and this helps Heisenberg equations borrow a similar character, but let's move on. And then there is something called, in classical mechanics, canonical transformation. This is like preserving an object. I will tell you what that object is. You start with a set of coordinates, as we did, and suppose you switch to other sets of coordinates in the same phase space, and then this is the Jacobian, as you know it. And then if it satisfies these properties, essentially just look at this one, then it's called a canonical transformation. So the takeaway from this page is that this canonical transformation allows volume to be preserved in this system. Volume elements will be preserved. Well, that's unsurprising because you see this determinant is 1. And such a matrix for a transformation is called symplectic matrix. In classical mechanics, they don't call it symplectic matrix, but we are anticipating the next discussion. All right, so finally, with all this said, I have mentioned it briefly that Liouville's theorem says that the volume of a region in the phase space does not change. So one can think of this as in fluid mechanics, like incompressible fluid. So incompressible fluid, volume acts like incompressible fluid. It doesn't change. It can twist the shape, but it cannot change the volume. So this is the detailed proof, but we don't need to go through that. Okay, and then now we are going to formalize classical mechanics into a better and more general framework called symplectic geometry. We're using classical mechanics as a basis to introduce symplectic geometry because it gives you something to work with at the back of your mind. So symplectic geometry has two objects, a manifold. It's an even dimensional manifold always, and then a certain structure, omega, and they satisfy the following conditions for the geometry. The manifold is a smooth manifold, and omega is a skew-symmetric bilinear form, which is antisymmetric, a skew-symmetric or antisymmetric. You might remember this when I was mentioning the beginning in classical mechanics. And then the other condition imposed on omega, the bilinear form, is that it's closed. That means d of omega is 0, or in 2 dimensions, easy to see. It means Stokes' theorem is preserved in 2 dimensions. And the last condition is non-degeneracy. That means the bilinear form, the skew-symmetric form, gives an isometry between the tangent and the cotangent bundles. Perhaps another way of saying the same thing equivalently is omega is when you wedge up omega, wedge up omega, wedge omega, wedge omega, n times, it becomes a volume form and it's non-vanishing. It should not be 0. Then it's equivalent to what I just said, non-degeneracy of the bilinear form. These are the conditions for a symplectic geometry, a symplectic manifold. We need examples. A typical example would be the 2n-dimensional real space, or equivalently, the complex n dimension, where they are related this way. Now, thanks to Doron, I can use this notation now, where j is repeated, therefore this is summation from 1 up to n in complex variables. Soon I'll write it in terms of real variables. Alternately, it doesn't make much of a difference, but this is a summation. So that means to keep in mind, you know that in this case you have zj and its conjugate are paired up, just like position and momenta. And this is an example. And any surface of any genus with area form is a symplectic manifold. S2, two-dimensional sphere, and the other with area forms, sum of area forms are also symplectic manifolds. Kähler manifolds are complex manifolds, but they can serve as examples of symplectic manifolds. And then a non-example is any of all spheres, only S2 is a symplectic manifold. So the other ones, none of them are symplectic. And the Klein bottle is not a manifold because it has no orientation. So, and regarding submanifolds, we will not dwell into this, but Lagrangian manifold people consider, for instance, if you remember, when I was pairing up variables, x1 paired up with x2, x1 with y1, x2, y2. So if you leave out the y's and work with the x1, x2, x3 alone, and similarly for the y's separately, then these are examples of Lagrangian manifolds, submanifolds. And then we need transformation between manifolds. And these ones are called thromorphisms between the first manifold and the second manifold with their respective binary forms, structures, omega 1, omega 2. And the condition is the manifolds are diffeomorphic to each other, and area, there is the pullback of the second form is the same as the first form. So that's area preserving in a way, because mind you, when you consider manifolds, a typical example is R2n. So you always have pairs, x1, x2 wedged up, so that little area in each pairwise component is preserved. That's what this means. Now let me give you a concrete discussion, which we'll go on with. There is a famous theorem in this direction. It's called the Arbus Theorem. It tells you that locally there is only one manifold, that is R2n, because they all look alike. And in real coordinates, this is what they look like. You see, this is the first element, the second, the third, and the last pair of area elements. So locally, you only have to deal with real. So that means there is nothing new you learn locally from any symplectic manifold more than you would in R2n. But there is some advantage while this is a lost advantage, there are lots of symplectomorphisms in symplectic geometry. That means you can start with, maybe let me switch to be able to write something on the screen. It's a slow writing is going to be. So when I was talking about symplectomorphisms, this is a slow writing. I hope you forgive. And a mapping, you can get such mappings that preserve the structure. And for instance, if you take H, you can call it a Hamiltonian x1 squared plus y1 squared over A, and I'll multiply by pi, just you will see why. And this is a symplectic convention. So if you consider this function h, then look at its level surface, constant, then it will be a circle, okay? Now, if you allow me to add more, x2 squared plus y2 squared over b, I multiply by pi, you'll see why I'm multiplying by pi. Then if I consider this as a constant, then the level surfaces are symplectic ellipsoids. And for instance, this portion, the reason I put pi in A is because one segment is area A, the other is area B. Then by working out this and trying to find this is xh, which the symplectic gradient. The symplectic gradient is J, the twisting form matrix times the gradient of h. Then this in 2 dimensions, this is in 4 dimensions, by the way, in 4 real dimensions. Then what this does is it gives you directions of motion. And this leads to a construction, although I'm not going to the details, of a mapping from the manifold, in this case to itself. And this becomes a diffeomorphism, and it's in fact area preserving, therefore a symplectomorphism. So you can get many, many functions like this. This is a Hamiltonian, this is the Hamiltonian flow, and this flow satisfies, this is the derivative with respect to time, satisfies dh or negative dh depending on the choice of the orientation. Okay, so bottom line is we have many, many symplectomorphisms in symplectic geometry. So let's move on. Now, from what I discussed earlier, at least in the classical sense, in the classical setting, Liouville's theorem says mechanical motions preserve volume. By the way, this means omega, wedge omega, and times, that's a volume form. So they preserve volume. And Arnold's theorem tells you mechanical motions preserve the symplectic structure omega. That means they preserve area. Now notice here, we have area preserving, here we have volume preserving. So a good question would be, and it has been asked, is what's the difference? Can area preserving diffeomorphism be volume preserving? Can volume preserving be area preserving? Or volume preserving diffeomorphisms, are they symplectomorphisms, and vice versa? Symplectomorphisms are indeed volume preserving, not the other way around. So the question is, how much a difference is there between the two? All right. From here on, we'll work with R2N and the classical, the standard form omega 0 that I mentioned earlier, or equivalently this way, it doesn't make much of a difference, because locally at least they are of that form, and for concreteness, we are going to move on with it. So the first question you ask is in 2 dimensions. That means n equal to 2. In R2, the structure, the symplectic form looks like this, that's it. And it is an area, by definition, it's a volume preserving, and any area preserving is volume preserving because area and volume are the same in this dimension, that's all. So there is nothing interesting here. Now, I'm going to continue, I'm going to introduce notations. In n dimensions, in general, we can talk about symplectic ellipsoid, and this, or this is a particular ellipsoid formulation. Once again, reminding me what Doran said, this is summation j from 1 to n. So this is like the ellipse equation that you know, except I used complex numbers. So in real coordinate, this means xj squared plus yj squared. So this is an ellipsoid here by definition. And any ellipsoid, even though you can twist them around, can be symplectically translated this way in an equivalent form. So this can be considered quite general. If all the A's at the bottom here are the same, you would guess, as you would guess, it will be a ball in 2n dimension or n complex dimension. Not just a notation. Now let's look at dimension 4. We have answered the question that there is no difference between volume-preserving diffeomorphisms and simplex homomorphisms in 2 dimensions. What about in 4 dimensions? Okay, is it possible to find a volume-preserving smooth mapping diffeomorphic to the 4-dimensional ball of area 1? Actually, it's possible. By rescaling, you can do that. But what's the problem? It's not, they are not going to be diffeomorphic. I mean, symplectomorphic, although they have the same volume. And the reason is that, okay, allow me to switch. The reason is the following. The first ellipsoid and the other ball, this is E1/2 and 2. So it has the same volume, symplectic volume, as the ball in 4 dimensions. Of course, everything is in 4 dimensions, radius 1. Another way of writing this one is E11, E11. Volume-wise, they are the same because the volume of EAB is A times B over 2. So the area, the volumes are the same. And a rescaling function can easily give you a diffeomorphism. But is it possible they are symplectically the same? No, they're not, because if you look at this cross-sectional area, it has area A, this has area 1/2. However, over here, this is area 1 all around. And like I mentioned before, this flow, Hamiltonian flow, actually in here, even in our setting, symplectic setting, actually introduces a flow around this, and you can people call it characteristic flow or characteristic foliation, and it brings in orbits. In this case, one orbit, for instance, is this way. The other harmonic motion is an orbit orbiting this way. But if you look at this one, the periods are the same all around. 1, 1. But in here, you have 2 different orbits at least. So they cannot be diffeomorphic to symplectomorphic, preserving the structure. So that means here is an example. I just finished talking about this. Here is an example that these 2 can be preserved. We can preserve their volumes, but we cannot say they are diffeomorphic. So they are different. So volume alone is not enough to characterize at least ellipsoids. Okay, if you cannot make them the same, then how about embedding? So the next question is, can you embed one manifold symplectic into another, and what can we say about that? Can you do that arbitrarily? That means, can you take a ball, for instance, and stick it inside any large size object symplectically? Let me mention one thing that's important is, if you recall, when I do coordinates, I have x1, y1, x2, y2, they're paired up, and this is a rigid restriction because if you want to twist a ball and stick it in a large volume, for instance, in this huge cylinder, you can do it, but you cannot do, for instance, twist it in the x1 and x3 direction. You have to preserve the x1, y1 area elements. So that's an important requirement. So Gromov's famous theorem in 1985 says you cannot arbitrarily squeeze in a given ball of cross-sectional area A into an arbitrary cylinder, there is a restriction. That little a has to be less than that big A. So it's called Gromov's non-squeezing theorem. All right, so now, then later on, several people got involved in this problem. Can we embed questions like, can we embed one ellipsoid into another? If we can, when can we do that or not? And also ballparking. I'll mention two results. The first result is due to McDuff, and that is, now there is something we give up. That is, embedding an ellipsoid into an ellipsoid is a tricky business if you consider the closed ellipsoid, because there is a symplectic structure, shadow, always lurking behind on the surface. The surface is a contact geometry on the surface. And then that will create a problem. Therefore, we always consider the interior of the ellipsoids. So can we embed this into this? They give a very nice condition, that is, if this numerical condition is satisfied, then we can do it. I'll mention I'll tell you what these numbers are. And for simplicity, I'll consider A, B, C, D to be integers. And let me see if I can erase this. Okay, I'm going to indicate to you what these numbers say. What are they, after all? They are denoted by N, A, B, and C, D. Let me say what N, A, B, C is. Okay. All right, N, A, B means, assume these are integers for now, positive integers, so to say. This is the set of all tuple, this is an infinite sequence, so that you have AX plus BY. You collect all these numbers by allowing X and Y to be non-negative integers. And here we must insist that this is a multi-set. If numbers are repeated, you have to repeat writing them. So for instance, N of 1, 4. If you do this, you're going to get a multi-set. Is it possible to get 0? Yes, I can get 0 by putting X and Y 0. Here, mind you, I'm choosing 1 and 4 for A and B respectively. And then can I get 1? Yes, I can get 1 once. I can get 2 once. I can get 3, but once. And then from here on, I can get 4, but I can get it in 2 different ways. And I can get 5 in 2 different ways. I can get 6 in 2 different ways. I can get 7 in 2 different ways. I can get 8 in 3 different ways. And so the next one will be 3. If you use generating functions, it is easy to see. Let me give you another one. Into 2, that means if I have 2 and 2.
Teddy, is that in the RIS, the coefficient of the generating functions of this?
Let me write the, thank you, Doron. Let me write the generating function for this at the bottom here. The generating function is like the coin exchanging problem. 1 minus x, 1 minus x to the 4. If we do expand this, we get 1 plus x squared plus x cubed. I hope I'm answering what you're asking. So I'll do one more. 2 times x to the 5. This is the expansion, the Taylor series. And then the way to read it from the generating function here is, so to say, generating function is, I have, this is x to the 0. So this is 1 times that. So I write 1, 0. I write 1, 1. I write 1, 2. I write 1, 3. I write 2 fourths. Does it make sense? Am I making sense, Doran?
Yes, I think so.
Is Doran here?
Yeah, that's so.
Okay. Now, n22, for instance, if I choose this to be 2, then this will, you can get 0, but you will never get odd numbers. So you'll have 2 2s. Then you get 3 4s. And you get 4 5. Let me not write this. And then the generating function is what you'd suspect, but you have to read it slightly differently than our usual reading of generating functions. So I'll leave this alone. 1 plus 2 times x squared, 3 times x to the 4, and so on. Okay, that's how we read it. Okay, now let me take advantage of this example I just wrote down. Then the theorem that I mentioned in the previous page, which I can come back to in a second, says that n14 is because it is less than n22. By that I mean coordinate-wise. This is bigger than that. This is bigger or equal, bigger or equal, bigger or equal, bigger or equal. Because that is true coordinate-wise, the coordinates you can write, we may write as nk of AB, by the way, in general. Then coordinate-wise, since this is dominating the first one, then you can say that an ellipsoid of side areas 1 and 4 in 4 dimensions is symplectically embeddable into an ellipsoid of side areas 2, 2, or a ball of dimension, a ball in 4 dimensions, B, 4, 2. That's what we did. That's the result of McDuff on the previous page. So these are numerical values that can completely characterize embeddings between 2 ellipsoids. Okay, so I can go back now to the slides. And the second result is the following. Okay, there are numbers. I hope to discuss this later, sooner. There are given a pair of numbers. Let's say for our discussion, A and B are integers, positive integers. The weight of a pair is another set of numbers we call W1, W2. With this notation, this theorem says, if you want to embed an ellipsoid into a ball, then it's equivalent to embedding a bunch of a disjoint union of balls into the ball that you started with. So that means if you can replace this by chopping up the ellipsoid into balls, then you can actually do the embedding as desired. I'm going to turn this into a numerical problem, so we'll come back to this later. Okay, maybe for lack of time, I'm gonna skip this. But I'll mention the following. If you remember, I have introduced this numerical sequence NAB. Suppose you have a sequence like that with infinite coordinates. You have another infinite set of numbers from a similar source. And now the connected sum of these 2 sequences is defined this way, where I plus j is k, and this is an infinite sequence itself. So the connected sum of sequences of any 2 sequences for that matter. And then regarding the specialized sequences from the previous theorem, by using Euclidean algorithm in some interesting manner, it's possible to break up a sequence like this into two sequences as a connected sum. Basically, without going into the details, this is a Euclidean algorithm. What does that mean? This means it's an ellipsoid of side areas A and A plus B. Then it is decomposable almost fully into a ball, because A and A are the same, and an ellipsoid, a disjoint in none of them. That's the bottom line now, by just cutting up an ellipse. And these numbers are numerical invariants. And now I want to, I can come back to this in a second. Okay. Okay, I can come back to this in a second. Let me relatedly introduce another object. People call this symplectic capacity. There are different definitions. This is one of them. It's an invariant. Suppose A is a number more than 1, this because we're going to stick as 1 and any number above or equal to 1 here. And then the question here, the number here is what's the smallest size of the ball, a ball, into which we can embed this ellipse. That number is denoted by C of A. Okay, but now I would like to translate this in terms of the numerical sequence we had before. That is, this is a new definition of an invariant. But earlier, this numerical sequence that is related to generating functions was discussed, but is there any connection between the two? Now, yes, I can write this as follows. Capturing this to be embeddable in here is the same as this sequence of numbers being dominated by this sequence of numbers. So we turn this into a numerical game. And the next observation is this number CA, the smallest it can be square root of A. In geometry, in symplectic geometry language, in terms of embedding, what it means is if CA, this capacity invariant, if it equals the square root of A, it means that when you want to do symplectomorphisms, the only obstruction is volume. So that means there is no change. There is nothing else to satisfy. So it becomes a very flabby condition. Otherwise, if they are not equal, then it is more rigid,
Eddie,
yes.
C of A is an integer sequence, right?
Sorry?
C of A is an integer sequence. C1, C2, C3. For every A, there's a...
Oh, Doron, actually, it can be anything.
Oh,
okay.
I'm a little bit lost. What is A? A is an integer?
Okay, let's put it this way. I think by its very definition, it is defined for integers, you're right. But the way we can look at it is as follows. It's a good question though. I'd like to go back. Yes, NAB looks like it's defined for integers, right?
Yeah.
Yes. And now what we could do is, now let me try to define it for fractions P and Q.
Oh, you extend it, yeah.
Yeah, for fractions P and Q. And then what happens here is I will have PQ, and then maybe I will have R over S. And then the beauty is that we will not be able to see things in this formulation, but going back to in the symplectic geometry, we can pull out this denominators. There is, what can I call, affine property, where you can pull out the Q, the denominators. Okay, that means the following. Basically, if I have 1 over 2x plus 3y. Let's make one of them integers. If I had 1/2 for A and 3 for the other one, then this is not what we have defined here by generating functions. So what we will do is multiply throughout by 2. Then you consider this problem, which is well defined in terms of our initial definition, right? Discussion. And then what about the 2 at the bottom? This can be pulled out because the capacity, it's called, the numerical sequences that are coming into the game are part of something called ECH capacity, which means embedded contact homology. Then it allows factorization of numbers without changing the embedding. So this way we can work with fractions, no problem. Of course, you have a more serious issue. What if I have an irrational number? Then in that case, if I have such irrational numbers, even this one being rational, I mean integer, then in that case, we'll replace this by its rational approximation, a series of approximations, and then try to embed them. If you can succeed with that in the limit, the embedding works for the irrational number too. So this is an extension from integers to rationals, from rationals to irrationals. I hope it makes sense.
Yes, thank you. Makes sense.
All right. So I think I need a punchline, so I'll move on. What this is telling you, for instance, is an ellipsoid 1, 2 is embeddable here, but this is absolutely obvious because you just include the ellipse inside the ball. There is nothing to do. Then this is a rigid condition. You cannot do better than that. So C of 2 is 2. C of 4 is 2 as well, strangely, because the reason is that when I considered earlier the numerical sequences 1, 4, and 2, 2, you realize that we were showing this to our actually, this is embeddable into this one. Although this one has a bigger volume, but sorry, not a bigger volume, a bigger size than this one, yes, bigger size. Nonetheless, because it is more oblong, it allows for twisting. So there is a flabbiness property, there is also a rigid property of this symplectic geometry embedding. All right, now let me move on to this. Okay, I prefer now, you can turn this discussion into the language of polytopes and Erhard function, but let me change, for lack of time, let me move here. Okay, what's going on? I'm going to change the problem completely into combinatorics. That is, assume you have a fraction like this. This time, true fractions, rational numbers, positive. And then consider the following problem. We can think of this as a polytope, that means a triangle, a right-angled triangle, right-angled triangle. One side is P over Q, the other side is Q over P, corner-wise, and one vertex at the origin in the first quadrant. Then we can ask the following. Of course, I can put 1 here if I want. Then I want to see what integers satisfy, what integer pairs satisfy this. I can ask this problem. That means, in other words, basically how many integer points, lattice points are within the triangle every time you inflate by t. So, example, if I choose P and Q both to be 1, then this is the number of lattice points inside a 1 by 1, an isosceles 1 by 1 rectangle, a triangle, an isosceles right angle 2 by 2, and so on and so forth. If we do that, then it is binomial coefficient n plus 2, n plus t, t plus 2, 2 binomial choice. So, but we ask the following question. for which other rational numbers will it be that the number of points, lattice points inside is the same between this and this? What numbers would make this work? Okay, the answer is surprisingly on the second page of my slide. For this to happen, P and Q as integers must be odd Fibonacci numbers, every other Fibonacci numbers, and their corresponding ratios. I'm sorry, forget ratios, that's another setting. So for this, this will be true, provided that these are pairs of odd, and when I say odd index Fibonacci numbers, of course. And another extra quantity that we get out of this is something called tau squared. The number 1 and tau squared in the ratio, where tau is the golden ratio. So another way of looking at this one is, instead of P and Q, look at it this way: P over Q and 1, P over Q as one coordinate, 1 here, and then this will be their limits as the index of Fibonacci increases to infinity. So this is an irrational polytope, but it has a polynomial Erhard function. Okay. I don't know, how much time do I have, Dora?
So this is necessary and sufficient that P and Q are consecutive odd
yes.
number with odd index?
Yes, no other rational number will work.
Ah, thank you. Interesting. And the tau square is tau is a golden ratio?
Yeah, tau is golden ratio, the square of that.
Yeah, the square of the golden ratio.
Yes.
Okay. But how does it relate to the question?
It's related as follows. You remember earlier on, I said when we considered the numerical sequence NAB, when we did that, this numerical sequence, I have A and B, right? And now, for instance, when I have N, 3, 4, for instance, if I scale accordingly when I'm trying to embed it somewhere else, let's say I'm trying to embed it into A and B, then here A and B, suppose they are integers, then embedding this one into this is equivalent to embedding this. N 3/4, 1, and the other one, N A over 4, 1. No, B over 4. Okay? According to this structure, it allows you, comparing this is bigger than this, is equivalent to in the embedding, I should say this E. Embedding this one into this one is equivalent to embedding this into this ellipsoid. So what does that mean? I can make this one 1 so that I can take fractions. Okay. In the page you asked me about, I was looking at basically E, PQ, assuming they're integers. Now I can make them, I can make one of them fractions for convenience, then PQ and 1. So from here on, I'm looking at only PQ, P over Q1. So that means embedding this.
Okay, so that's the limit.
Yeah, and then I take the limit. That's right.
Okay, thank you.
I take the limit, right. That's right. So for lack of time, I think I have something, but it is 15 minutes. I have to oblige Goron's axiom.
Thanks so much. Please unmute yourself and thank Teddy. And we have time for a couple of questions. Are there any questions? So I have a question.
Yes.
Edusa McDuff in a colloquium, AMS colloquium talk about 5 years ago, talked about it. So I was very excited that how this fancy geometry and symplectic geometry combinatorics comes up. So the stuff that you mentioned at the end is new that you did?
Okay. The new part is the proof that they give is symplectic geometry technology. But I consider this problem right here and prove it in an elementary fashion.
Interesting. So you have an elementary proof of this?
Yeah, elementary number theoretic proof.
Yeah, oh, that's nice. And is there any way to have extensions of this? It
is possible. It has possibility, but for instance, just like you have Fibonacci numbers, there is possibility to also get other numbers like Pell numbers by a different setup. And then I'm looking into that if the proof works.
Interesting. That'd be nice. But what if it changes in the right-hand side, the number of z sub t, 1, to d sub t of something else? For example, 1,2 or 2,3. Do they exist analogous optimization?
You mean here, this number?
Yeah.
That's an important question. Actually, when I have more numbers here, actually, I'm looking at, instead of 4 dimensions in the geometry, I'm looking at, even if I add 1 component, I'm looking at 4 dimensions. No, 6 dimensions. Or 8.
Yeah.
Even in the 6th dimension, or 8, or any other higher values, this background technique that made it work for the geometry people, it's called ECH capacity, embedded contact homology capacities. They are only work due to work by Witten and others. They only function in 4 dimensions, unfortunately.
Thank you.
So these problems are wide open in higher dimensions.
Okay. Any other questions? Well, let's thank Teddy again, and thanks for a very, very interesting talk combining this very fancy highbrow mathematics with down-to-earth combinatorics. And everything is combinatorics. Once again, it's a proof. Thanks so much.
Thank you.
Thanks for coming, and thanks for the great talk. Thank you.
Thank you.
This ends this meeting.